Okay, so we're going to start with this example of how we find the flux of this three-dimensional vector field through this 2D surface. So go ahead and put this on pause, and what I'd like you to do first is just try to sketch the part of the surface that we're even talking about. Okay, so here's one way we can visualize this. And you notice that this surface here is going to be a cylinder, but we're cutting that off. So I really only want the part here that is bounded by z equals 0, x equals 0, and x equals 1. And so really I'm just asking about the flux through this yellow band here. That's the surface S that we're talking about. And then I have a vector field. We haven't visualized it yet, but I'll just randomly draw something on here that's not the vector field. But just imagine that we have something that is flowing around or through this region, and we would like to know what's the flux through this surface. Okay, so we have several steps. First step is to rewrite this surface as one level surface of a function of three variables. So I am going to do that by just picturing, I'll write it here. I'm just going to picture G as being y squared plus z squared equaling 4. And here again is the surface that we're talking about. All right, and then I want to find the normal vector. And so when I take the gradient of this G, I'm going to get 0, 2y, 2z. And I need to double check that that in fact is going to give me something that is normal to this surface and pointing the correct direction. So again, when we say the flux, our default orientation is outward from any curves, like as if we were to allow this yellow band to continue to form like maybe a whole solid region, then I'm talking about just the outward flux. So notice that my n in this case, if I just plot it, let's just plot it here at this point where I would be on the surface. This would be the point y is 0, z is 2 right here. And if I plug that in, my gradient right here, y is 0, z is 2, is going to be 0, 0, 4. And so it is in fact pointing the correct direction. So I don't need to take the negative of it. I can just use the gradient as I found it. And again, the reason you need to check that is there's a lot of different ways I could have written this as a level surface. I could have thought of this as being 4 minus z squared minus y squared equaling 0, and I could have let that be my G. And if that had been the case, then my gradient would be pointing the wrong way. So remember, there's more than one way to write this as a level surface of a function of three variables. And so that's why you want to check that your gradient is pointing the way we want. Okay, and then you're going to pick a plane to project this. And again, what you want to do is imagine this little yellow band, imagine flattening it onto one of the coordinate planes, and you don't want it to fold onto itself. So really the only coordinate plane where it's not going to fold onto itself or be an issue is the xy plane. Because when I flatten it, the shadow is just going to be this rectangular region. Notice if I had tried to flatten it onto the xz plane, it would have folded onto itself, because here's the xz plane, and so this half would have folded onto that half. And if I had tried to do the yz plane, it would have smashed down like it was like a slinky smashing down, and I would not even have a two-dimensional shadow. My shadow would just be this one-dimensional curve. And so I would lose the information about the surface if I did that. So I need to flatten the surface onto some region in the or onto a plane where I will get a two-dimensional region that I can integrate over. So that's why we're going to just flatten it onto the xy plane, and my region R then becomes this rectangle. Okay, now let's go to the next steps. Step 4 is I'm going to convert my integrand. So I have f dot n ds, and f was given to me up here. N I have found here, ds we found back when we first did surface integrals. And now I'm just noticing that these gradients are going to cancel, and I'll simplify from here. So this is going to give me y squared plus z squared dA. Okay, now I need to make sure that I convert this to be in terms of the variables of the plane where I've projected. And so I've projected onto the XY plane, but right now I have things in terms of Y and Z. So I can't leave them like this. I need to go back up to the equation I have for the surface and put things in terms of X and Y. So notice the surface is Y squared plus Z squared is equal to 4. And so I can use that to rewrite this integrand as just 4 dA. And then I'm ready to integrate 4 dA over this rectangular region in the XY plane. So now it becomes a double integral problem like we've seen last chapter. And oops, either way that I do this, I'm going to end up getting 16. Notice what I could also do if you don't even want to set up the bounds is you realize it was going to be 4 times the area. And the area of this particular rectangle was 4. So I'm ending up with 16 total. And again, what that's telling me up here is if you imagine water or something flowing through this whole region, that's telling me the net outward rate at which the water would be flowing through the surface. And the units in this case is going to be meters cubed per second because it's now giving me like the little volume of water that would be passing through in a given time period.